How do we solve for the internal loads in a 3D structure? The first steps are going to be basically the same as we took for 2D. We generally want to solve for the external support reactions first before we do anything with an internal cut. Then we want to locate the point at which we want to know the internal loads, and then we're going to make a section cut, usually perpendicular to the longitude of the member. Then we're going to take one side of the cut or the other. Again, generally we want to take the side of the cut that just has less going on, so there's less to write in our equations. And then we're going to draw a free body diagram for the section that we just created. On that cut surface, we've now exposed 6 internal loads when we have a 3D shape. So let's look at these internal loads that we can now see now that we have separated one section from the other. So first, we have coming out from the surface of our cut, we have that internal normal force P, like we did in 2 dimensions. Always, the direction of P is going to be the outward normal from the surface of the cut. In this example, that happens to be the positive y-axis, but only because the positive y-axis is the direction that is outward normal from the surface of this cut at point C. And this internal normal force P is coming out through the centroid of the cross-section. Like in 2D, parallel to the surface of the cut, we're going to have a shear force V. Now here we are going to immediately break it down into component form, so 2 components of that shear force. In this case, for convenience for going into my equations, I'm going to say there's a component of V along the x direction and a component along the z direction. It is not always along x and z, but here, because the outward normal is y, and we know that then the shear force is in the xz plane, I've broken it down into an x component and a z component. We have the internal torsion, T, and we are always going to draw that around the axis that P lies on. So in this case, P lies along the y-axis. T, we are going to say, is positive counterclockwise around that axis. In this case, y. The direction of T and P is always determined by the outward normal direction from the surface of the cut. And then finally, in the plane parallel to the surface of the cut, we're going to have a bending moment. And like with the shear forces, we are going to immediately break it down into its components. So in this case, there's a component around the x-axis, counterclockwise around x, we'll assume, and a component counterclockwise around the z-axis. The v and the m will always share the same component directions. The p and the t will always be acting along that same axis. And our interpretations are going to be similar to what we saw in 2D. P positive is always going to indicate that it's a tensile internal normal force, and a negative value for P will say it's compressive. We're always assuming T is positive around that positive P direction, and we only use these global axes for the shear and the moment components. In this case, we know they act in the xz plane, so we're making a v sub x and a v sub z. Same thing for m. We have an x component and a z component. And in this case, all these subscripts are there because P is along that positive y-axis, but the global coordinate system that we use could be different in a different problem. So in a problem where P happens to be along the positive x direction, then we would have a v sub y and a v sub z, an m sub y and an m sub z.